Hello, everyone, and welcome to the first lectures in a series of lectures on the calculus of variations. I'm very excited to be teaching this course right now. It's one of my favorite courses that I took when I was an undergraduate, probably my most favorite, because it's a course that really emphasizes the direct connection between mathematics and physics and applications. And it's really some beautiful mathematics as well as beautiful in its applications to physics and engineering. The main textbook that we'll be using for the course is The Calculus of Variations by the authors Gelfand and Fomin. And this is a Dover book on mathematics. So it was published by Dover in 1992. Originally, it was printed in 1963. It was originally published, and it's a fantastic reference to both the applications and the basic theory of the calculus of variations. Um, the original version, the 63 version, is available for free online from the Internet Archive. So I recommend you going to find that copy online because it's essentially not that different from the Dover edition. However, the Dover edition is a fantastic thing to purchase. It's I think less than $10 for the Kindle edition. So I sincerely recommend getting a copy of it, a hard copy, but it's available for free online. Um, there's three other texts that I recommend as very good texts as well that can sometimes give alternative explanations and new examples that would be very, very helpful. That's Methods of Mathematical Physics by Courant and Hilbert. The Calculus of Variations material is in Volume 1, Chapter 4. This was originally printed in 1937 and reprinted in 1953, 89, and 2004. Um, this is a fantastic textbook in general for topics in mathematical physics, and is a classic text for explaining many things, but specifically it has a great section on the calculus of variations. The book Calculus of Variations by Lev Elsgolk is the third reference that I think is a fantastic reference. Originally printed in 61 and reprinted in 2007. This is another Dover book on mathematics that I sincerely recommend. I believe it's the original version is available for free on the Internet Archive. In the fourth reference is Introduction to the Calculus of Variations by Hans Sagan, originally printed in 1969, and then again reprinted in 1992. This is another Dover book. But we will be sticking in this class with the Gelfand and Fomin text. These other three texts are very, very good references for you to look at if you have further questions. And so you may be wondering what exactly the calculus of variations is and what it's about. Um, most simply put, the calculus of variations is the study of extending calculus from functions of one real variable or from functions of, say, multiple real variables, so multivariable calculus, extending that study to things that are called functionals. Um, a functional is a mapping from some set of well-defined elements into the real numbers. A set of well-defined elements is admittedly a little bit ambiguous. However, this will be explained later on what this means when we start getting into the method of solving problems. Typically, though, in the calculus of variations, this set of well-defined elements is a function space. And this is going to have certain properties that we need to kind of look at and understand a little bit better when we start diving a little bit deeper into the theory. However, if S is, say, the set of real numbers, a functional is really just a function from R to R, so the real numbers to the real numbers. If S is two-dimensional or three-dimensional Euclidean space, or even n-dimensional Euclidean space, then the functional is just a standard function from that set S into R. Things become very, very interesting for us when the set S of well-defined elements is an actual function set, so a set of functions. So we'll do some examples in a little bit, but I just want to emphasize this notation here. So we can call a functional by any letter we want to. However, a very common letter to use for a functional is J, and we say that the functional itself is a mapping from the set of well-defined elements to R, such that for every element in this set, there corresponds exactly one number, A, in R, which we call the value of the functional at the element S in S. The notation for this mapping is standard mathematical function notation, which is that J maps the set S into R, and the exact mapping, we typically write J of S equals A, or the element S in S maps to the element A in R. So let's just do some quick examples. For instance, if S is two-dimensional Euclidean space, the functional is really just some multivariable function of two variables, because we're saying that J is a mapping from S into R. So anything of the form, say, F from two-dimensional space into R is a valid functional. For example, you could choose the function f of xy is equal to x times y times sine of x squared plus y squared. This is a good example of a functional from two-dimensional Euclidean space into the real numbers. It's just a function of two variables. Even simpler, let's say S, the domain space, is equal to the real number line. Then the functional is really just a one variable function from R into R, the typical function that you see in calculus. Calculus 1, that is. This would be a multivariable example. This example is just a single variable calculus example. So say, for instance, f of x is equal to x times e to the negative x squared. These are both good examples. Where the calculus of variations begins to get interesting and much different than normal calculus is if we say, consider the following example. This is the example where the set of well-defined elements, which I'll make clear what well-defined means in a few lectures, is the set C of AB. And I'll put in words what this is right here. This is the set of continuous functions on the interval AB. So the set of all functions that can be expressed as a continuous function on the interval from A to B. So a good example, just to give you a concrete example, would be the functional I of y is equal to the definite integral from 0 to 1 of y squared dx. This is a functional from this set S into R, because for any different function value, for continuous function, this will give you a different real number. For instance, if you take I of x, this is going to give you the value integral from 0 to 1 of y equals x for when y equals x. So I of x is going to be just integral from 0 to 1 of x squared dx, which will have the value of the antiderivative of this is x cubed over 3. This is the fundamental theorem of calculus here. Evaluated at the boundaries, 1 and 0. When you plug this in, you get 1/3. So for this example functional, evaluated at the function y equals x gives you a value of 1/3, whereas if you take this functional and you evaluate it at sine of pi times x, this functional evaluated at the function sine of pi times x will be the integral from 0 to 1 of y squared. So it'll be sine squared of pi times x, which we can integrate using standard integration technique. So using the double angle formula, sine squared of pi x will be 1 minus cosine of 2 pi x over 2, which when we do the antiderivative of both of these terms will give us, we can pull the 1/2 out. This will become x minus 1 over 2 pi sine of 2 pi x from 1 to 0. When you plug in the bounds here, this entire thing reduces just to 1/2, which is a different value than the functional evaluated at x. But I think this clearly shows the idea. For another example, let's say we'd like to change the set of admissible functions, as it's called, set S, and we'll say S is the set C1 on the interval from a to b. And this set is the set of continuously differentiable functions. On the interval from a to b. And this means that the function, anything in S, this set C1, if the set C1 is both continuous and its derivative is continuous. So for example, you would consider the function I of y equal to the integral from 0 to 1 of y squared plus y times y prime dx. This is well defined because anything that you plug into it, as long as y is continuously differentiable, its derivative is continuous, and therefore the function that you get here is integrable. So I'll use the same example functions from before. I of x here will give you the integral from 0 to 1 of x squared. This is when y equals x. You have x squared plus x times 1, because 1 is the derivative of the function x, dx, which is x cubed over 3 plus x squared over 2, evaluated from 1 to 0, will give you a value of 5/6 for the functional. So this new functional at y equals x has a value of 5/6, and when you compute this functional at sine of pi x, this is going to be the integral from 0 to 1 of sine squared of pi x plus sine of pi x times the derivative of sine of pi x which is pi times cosine of pi x dx. This is a little bit longer than before, but essentially this is what we get for this functional, specific functional right here, when we evaluate it at the function sine of pi x. You can use the same method as before to get this integral, the antiderivative of this function, for the sine squared portion at least. So we know that sine squared portion will end up, this entire integral will be 1/2. So it'll be 1/2 times the integral of sine of pi x times pi times cosine of pi x, which can be evaluated via u substitution. So after a u substitution of u equals cosine of pi x into this integral right here, the integral of sine squared from 0 to 1 is 1/2. And when you do the u substitution here, you end up getting that this is going to be the same thing when you do this integral as negative 1/2 cosine of pi times x squared from 1 to 0. And this ends up just being 0 when you plug in 1 and 0. You get a cancellation here. So this value is just 1/2. So this new functional evaluated at sine of pi x is 1/2, similar to the previous functional, but it's a completely different functional. And I think this is, two very clear examples. So at this point, you may be wondering why these things are so important. Why on Earth would we want to generalize calculus or multivariable calculus to the study of these functionals? And the main answer to that is because of real-world optimization problems, so maximum and minimum problems. Very, very often, and I would go so far as to say almost always, in physics or in engineering, or in even other areas of applied sciences like computer science, an optimization problem is most correctly stated as what's called a variational problem, or a maximization or minimization of a functional problem. It's solving for the best function in some set of functions that maximizes or minimizes a functional as it's written down. And the solution to this problem will give you, say, in some sense, the optimal solution to the given problem. It turns out that in physics, variational principles are actually manifestations of very general physical laws, which are valid in diverse branches of physics, ranging from classical physics all the way to subatomic particle physics and quantum mechanics. So what I'd like to do is just list out and talk about some of these applications, just to kind of keep you motivated to learn the mathematics. I think it'll be very helpful to kind of touch on as many applications as possible, even if we can't get into the details just yet. So the first main example where functionals show up in application is to say, what if you want to find the path that minimizes traversal time or traversal distance when going from a point A to a point B. So you start at some point A, and you want to travel to some point B under some constraints. One of the exercises that is a good exercise to go through and do is to actually prove that in normal Euclidean space, the shortest possible path between 2 points is a straight line that minimizes the distance between those 2 points. It's something that geometrically it should be a relatively straightforward thing, but this can actually be proven using variational principles. However, this is not always the case, depending on what it is that exactly you want to minimize. For instance, if you have some sort of other constraining equations on the motion, the shortest possible path may not necessarily be a straight line. For instance, let's say you want to figure out the path which minimizes the time of traversal, and you have some constraint equation or some sort of constraint equation constraining the physics of motion along the curve which you're traveling in. For instance, one of the first problems that we're going to consider is the brachistochrone problem, where you want to design a curve or a path for some falling object that minimizes the traversal time as you go from A to B. It turns out that the optimal path looks something like the following. It'll look something like this, where you have an infinitely steep slope starting off, and then gradually, over the course of the run, this kind of tapers off and goes to be like this. We'll see this as the first example, and it makes sense that we're going to use this as our first example when we get into it in the next lecture, because this was actually one of the first main problems that was brought to the public attention back when this problem was introduced. So this is a good example of a problem where you don't necessarily have a straight line solution. Another example would be, say, if you have a light propagating in a certain medium and you have a change in your medium. So let's say you have some interface between A and B where to the left of this you have material 1, and to the right of this you have material 2. Fermat's principle says that light must propagate in the path of minimal time, and so let's say that path of minimal time in 1 is going like this to right here, and then maybe goes like this from right here, this interface point right here, onwards. So the problem would be to find the relationship between these two paths, specifically where this point is right here and what the angle is, angle of incidence versus the angle of refraction. And this is actually known as Snell's law and can be proven using the calculus of variations. We'll see that later on in the course. So there's many interesting solutions to certain problems where the path is not this optimal path is not necessarily a straight line. Another really good example is the idea of a geodesic on a manifold. So if you take a general manifold, so some surface, say, I'll just draw kind of like a 2D surface here. Let's say this is some surface, and we'll just call it M for short. And let's say you want to find the path on this manifold that gives you the shortest possible path, or the curves on the manifold that are the shortest possible length to get from 2 points on the manifold. You want from, say, A right here to B right here. This is a very interesting topic in differential geometry, but it has real-world applications in general relativity, because the geodesics in general relativity correspond to what are called world lines. One of the fundamental principles in general relativity is that the world lines, or the path that particles traverse in general relativity, are geodesics of the underlying space-time manifold. So this is a very interesting, very advanced application. The final application here of this first kind of subset of applications is maybe in robotics. You want to say maximize or minimize the trajectory of a robot arm with respect to the input controls. This is a fantastic example. For the next set of applications that I'm going to discuss, you could consider finding the shape or a curve or a surface which maximizes or minimizes some geometric or physical property that you might be interested in. For instance, you can think of the classical example of a soap bubble. If you take, say, two separate rings that are connected via a thin film of soap, so like say a ring 1 right here and a ring 2 right here, you could ask yourself, what is the curve of minimal surface area? And it turns out that this is exactly how the problem of the soap bubble was first kind of introduced, as a surface of revolution of minimal surface area between these two curves. There are many other types of problems that you can consider, say finding the maximal area bounded by some curve. If you have, say, a line L and you have some curve or some function, you want to figure out what exactly is the function that maximizes the area contained inside that curve. This is the so-called isoperimetric problem, and it's another problem that we're going to be talking about as we move on through this course. The next set of examples is from physics, and really any physical system in some sense can be described by classical mechanics, general relativity, quantum mechanics, and in general field theory, which are all examples of using variational principles to derive the equations of motion or the governing equations of a physical system. In classical mechanics, specifically in Lagrangian mechanics, you have this thing that you call the Lagrangian, which is essentially the kinetic energy of the system minus the potential energy of the system. And it turns out that for physical systems, the stationarity conditions for the Lagrangian functional, Lagrangian is a functional, it depends on the trajectory of the system, in trying to find the stationarity conditions of the Lagrangian will actually give you the equations of motion. So you can get Newton's laws of motion from investigating the kinetic energy minus the potential energy of any classical system. But these ideas are even further beyond just classical mechanics, because it turns out, as I mentioned earlier, with the idea of a geodesic in general relativity, it also shows up in general relativity very, very strongly. And not only that, but in modern quantum mechanics as well, the idea of a field in field theory is where the calculus of variations is extremely, extremely important to understand. And all of these applications have a central functional of study, which then determine the evolution of a given system. The final set of problems, which actually go beyond traditional calculus of variations, are called optimal control problems. And essentially, these break down to problems for which you have some sort of differential equation or system of differential equations that govern some process, and you wish to determine the inputs to the system which maximize or minimize some desired functional. For instance, let's say you want to figure out the best way to fly a rocket to get from point A to point B in minimal time, and what the optimal input functions are for the rocket flight. And maybe you have some sort of constraint as well, like the maximum amount of fuel that you can use is a certain value. Or for instance, let's say you have some robotics problem where you want to move some robotic arm or some robotic contraption in some optimal way, and you want to figure out the optimal way of kind of inputting the controls of the problem to get the optimal output. You could also construct many problems like this in economics or in finance as well. So economics and mathematical finance. This is a remarkable theory, and it has fantastic ideas and solutions to problems contained within it. Um, so this is another very good set of example problems that we'll be using towards the end of the course. But I think that will be all for today's lecture. I hope you learned something and had a fantastic day.